originally an academician before, and but now I switch to Foseco as the global R&D manager responsible for non-ferrous metal treatment, which mainly covers aluminum and magnesium, copper, and other sorts of non-ferrous metals that helping foundries resolve some problems and also get the best casting quality as possible with the lowest defects, porosity inclusions, and achieve highest yield as possible. So that's my responsibility in Foseco. So that's who I am. Yeah.
So you were an associated professor in Turkey, Istanbul, and then you moved to Netherlands.
Yeah, yeah, true. I actually, yeah, I had my PhD in Birmingham in UK, and then I moved to Turkey, Istanbul University as an associated professor. Then I moved to Norway, NTNU University, and worked as a scientist, senior scientist in an institute called SINTEF in Norway. I spent 5 years there working with all foundries around the world, and then Istanbul Technical University, and then I am here. Yes.
Yeah, I would like to continue with the agenda and briefly introduce what are we going to talk about today, and then continue with your presentation. Is it okay, Derya?
Yeah, sure. Yes, let's go ahead.
Okay, today we just had this introduction, and of course we'll continue with Derya's presentation, and he will explain why material matter, and we will briefly introduce Total Materia. And of course, we are expecting your questions from the audience. Please do not hesitate to send us your questions.
Yes, I need to share my screen now. Yes. Yes, so the basis of all new products, almost 70% of new products are based on new materials. So the more the new materials we find, actually, the more application areas, the new things come up. And the latest new materials that I could find that I think is quite critical in terms of material selection and design are graphene aerogels, artificial webs, super glues, transparent ceramics, metal foams, and metamaterials, and also 3D printing of almost any type of material has become so popular. So finding of these new materials, and most of them actually were found by accident. That's also the funny story of history of materials. None of them were ever found in a aim to find this material, but working on some subject and suddenly finding these materials. So that's also an I would like to deep note that funny anecdote that none of them were found by knowledge, or it was all by surprise. So these are all changing our lives, so knowing the materials. And I really love this histogram, or the history of ages, because they all are named after the materials. So Stone Age, Bronze Age, Iron Age, Steel Age, Silicon Age. And for those of you who doesn't know me, I am expert, and my expertise is in aluminum, actually. So I would like to request a new era somewhere here, because aluminum has changed engineering forever. Yeah. So there, I hope I will change history and put aluminum age somewhere here as well. That's my goal with the historians and everybody. So as you know, yeah, as we can see, all the ages in the history are based on materials. Yes. Well, when it comes to design, it is defined as the process of translating a new idea or a new market need into a detailed information from which a product can be manufactured. So that's what design is defined as. So we have to have an idea, or there should be a market need. And in that sense, actually, we have this very famous octagram, we should have a structure. That structure has to have certain properties, and that properties will result in a certain performance, but it has to be produced by a certain process. So in that sense, when we are designing, the product should have a weight. Yes, it should maybe carry a load, you know, or maybe conduct heat, conduct electricity, has certain wear properties, corrosion properties. So our design has a function, it has a geometry, there is a material, and it should be produced by a process. So that's
So you need a lot
basically
of alternative materials and a lot of materials information.
Exactly. We need a lot of information. Yes. And so the diagram actually goes like this, as mentioned previously. So there is a market need, therefore there is an idea, and in the idea stage there is list of all materials, and then there is an embodiment. We get narrowed down to subcategories, and after that we need to find the function, suitability analysis, you know, optimization, some cost analysis, and then we go into a detail, and in the detail we have the single material, and from that single material we have our product now. But there is also a cycle of this improvement, like as we have seen in the previous slide. Yes, there was a need, there was all data, we have the concept, and then less data, and then a single data when we found our product and we start producing it. But this is not good enough, just producing and putting it in service, because in service, after the production, it should be used. And after the usage of these materials in any sort of application, there is a certain life. So in this cycle, everything seems so perfect up until we make the design, make sure that we selected our material and we produced it. It's okay so far, but in the usage, we need to make sure when it fails, how it fails, when it fails, why it failed, and we answer all those questions. So we have the life of this material in the application, and then we can do reanalysis or redesign, maybe change the design or maybe change the material, and then try to extend this as best as we can. So this is, as I mentioned, like is the critical point, the life, because from there, when the material is selected and produced and in use, we get more information actually, because we start to understand how it works, why it fails, how it fails. So from that, we can change our materials or our design, but also based on the, as we mentioned, evaluation of our materials. For example, the glass was initially used as liquid containers, but glass was a little bit heavy. It's healthy, but heavy, but brittle. So we changed into plastics now, and we can even recycle plastics now. And steel actually was used as food containers. Well, I can say that it was slightly heavy, but not corrosion resistant. So we need to apply several different coatings, or several precautions need to be taken in this design so that the food life would be extended as late as possible. But with the finding of aluminium, yes, it became lighter and more food friendly, and so
corrosion resistant.
corrosion resistant, and no toxicity as well. So like in this life cycle, as I mentioned, like the funniest example that I found on the internet was this picture. I really liked it. If Titanic sinks today, everybody will be taking the pictures. But this life cycle is like most of the things, like we think that it is the best suitable material. We can produce it, we can have it in use, but suddenly we came across a very dramatic failure. And then we started to understand the impact properties of materials at different temperatures. So we developed new materials so that they can survive under these circumstances.
Standard range. Even if you have an estimation, experience, or knowledge, still you know the material on the field.
Yeah, exactly. That's the most critical thing, actually. Yes. So producing, selecting the alloy by itself is not enough, actually.
Yeah.
And for these materials, there are, well, this looks like a tensile testing, mechanical test, but I'm not only talking about mechanical tests. I'm talking about all sorts of tests where we can determine the properties and characterize the properties of our materials. A lot of tests are done, a lot of results, a lot of data. Then from those data, statistical analysis, and now we have our design values. And from the design values, we started to select our material, look at the potential applications, how we can produce, cost analysis, and then hopefully successfully use them in several applications. So this is also the kind of a cycle that we follow for material selection.
So standard material properties are not enough under the specific conditions.
Yeah.
You need to test the materials and have to have this data.
Exactly. Yeah, true, exactly. So, for example, in airplanes, in passenger airplanes, because they only lift off and land, so there is almost one directional movement for passenger airplanes. So the forces that are applied and subject to the materials in the passenger airplanes are almost in simple directions. So what we do is we characterize these properties, and based on these properties, we know that up to 50,000 or 100,000 hours later, we do our checks and maybe change the part. But for fighter aircrafts, this is 600 hours. Sorry, 6,000 hours. The main reason is that because the forces applied on the aircrafts, because of their agility and all these maneuvers, the forces are coming in many different dimensions and with many different strengths and values. So our material has to be different that we choose.
Yesterday we were talking about fatigue when people find out that, because even if you have a lot of properties or you make design, like it's okay, it will stand forever, like. But then engineers find out that there is a thing exists, and it is fatigue. Actually, it's happening. Microstructural cracks becoming all in once, and then all of a sudden, failure comes out. Like in airplanes, it's unacceptable.
Yeah, true. So this is also an interesting information that I found on the web. We used to know as a kid, like read stories, kid stories, that the ants were the strongest animals. They can carry a lot of weight. But this bug called Ornithophagous thaurus is about 10 centimeters tall height, and it can carry 1,141 times its weight. So actually, an average human can step on it, and this bug can actually carry it, which is 10 times more than an ant can carry. So these are the kind of things that, like finding the new materials and finding an application area.
This looks like an armed vehicle.
Yes.
Tank, yeah. Tank of the box, yeah.
Yeah, so materials, these are just basic informations. Like, as we all know, we classify materials as metal, ceramic, glass, plastic, and composites. And each of them, there is always a general knowledge. Like metals, as we know, aluminum, steel, iron, magnesium. And we know that they have high electrical conductivity, high thermal conductivity. They can be ductile, easy to shape, and cheap to produce. Ceramics, low electrical conductivity, low thermal conductivity. We know they are mostly very brittle materials, and usually we select these kind of materials in high temperature applications for their certain properties. Same with the polymers, low thermal resistivity, low electrical resistivity, easy to shape. Composites, combination of these two, at least two different materials, and they have low density, high strength, and typically they are known to be a little expensive materials. So when we are making a material selection and design, there should be several questions, like what's the physical and mechanical properties of these materials, and how can we produce it and give the final shape to this design, and what would be the cost of this. And lately it's been very popular, as we all know, the environmental facts, CO2 emissions, sustainability. So what are the environmental facts of these materials that we are going to select, and also the process that we are going to apply to produce this final design becomes quite critical. So these all questions have to be evaluated when we are making a selection. And the most famous material selection method is being proposed by Ashby. So it goes through like 4 stages. So first stage is the translation. So we need to know the function. We need to have the objectives. Do we have any constraints? For example, we cannot go higher than 10 kg for this part, or this cannot be more than 1 meter long, or this. So we should have the constraints, and we should also be able to have free variables, so that in that sense, we can think about the geometry, the design, the shape, and everything. And then the screening, which is eliminating the materials that will not be able to do this job, and then ranking the list of best possible materials that can do the job. And there is also always an additional information like the existing or similarly functioning materials in the use. So those kind of informations can lead us to finding the best material that we can choose. And there is also the performance equation that can be used, but this equation can be converted to many different parameters. For example, a simplest example here we can see is the strength is always the force over the area, cross-section area, and mass is density times the volume. And if it's a cylindrical part, then we have the length and the cross-section of the area. And from all these equations, we can change many different equations and just put them in a single way. For example, in this example, we have mass should be greater than, so here instead of area, we can put force over the strength of the material, and then the formula becomes the force that's applied to the material, the length of this material, and what we call a performance index, which is the density of the material divided by its strength. So here in this example, the performance equation is the weight. Probably there was a weight reduction requirement for this, but it had a certain force being applied on it, and it has a certain length. So these are like our functional and geometrical parameters that were fixed, as was mentioned in the Ashby methodology. So what we can do is play around with this. So if we want it to be lighter, so we need to find the material that has low density with the highest strength. So those kind of mathematical or those kind of approaches can be done to find the best material depending on the need.
So it's all
yes,
about
the selection of the right material.
You know where it's going to work. So you have all this data,
yeah,
but then you need to find the most accurate material for that design.
Exactly. So like in the Ashby methodology, there are certain functions, like if it must conduct electricity, then I need to look at the conductivity of these materials. If it has to carry a load, then I need to look at the strength. If it must be cheap, I think this is always the case. So I need to look at the cost of production. So how do we do that? Actually, we look at books, we look at publications, we look at tables, databases, manufacturer catalogs, and all these data can be found easily, and these can help us, aid us on our selection. I wanted to put a question mark next to internet, because internet is, yes, actually all of these things we can find it through internet, but we need to be really careful when we are doing research on materials, because they have to, the information has to be reliable. So we need to make sure that this is a standard test, or this has been carried out by certain conditions, not just Googling through the internet and finding the best material. No, we need to make sure that every data that we find is reliable.
Derya,
so in that case, yes.
Yeah, just to tell you and the people that are inside this webinar, Google is a customer of ours. They use our Total Materia reference data Their engineers don't even use their own Google browser. So their engineers use our platform.
Don't Google it for accurate information. Yes.
Yeah. So that's why I said more reliable sources. Make sure that it is a reliable source. So not because, I mean, as I mentioned, I was academician before, so lecturing and working in the universities with students. Sometimes you give homeworks and they come up with very interesting results, like, hey, how did you find this information? Well, I found this in a forum, in a discussion forum. Okay, the forums and discussion forums are, everybody says something. I mean, even Wikipedia, for example, as everybody knows, Wikipedia is a personally editable link, and as long as there are some references given below, maybe you can follow those references. So Wikipedia could only give you an idea and an information, but never use Wikipedia as a resource or a reference. So it's like, that's what I mean, actually, to be specific. Yeah, so we were talking about database and data. So here comes you guys, Total Materia. Yeah. With all the detailed information. So I don't know what, maybe you would like to say something about this, guys.
Absolutely. So Derya, you were talking about material selection. Yes, maybe finding an equivalent material which is cheaper to use, which is more available, finding real data coming from real references, coming from standards. Most of our information that we provide is coming directly from standards, but also trying to understand the materials that you're looking at, analyzing them, comparing them. But even all the way at the end, I was kind of happy to see you write this in your presentation as well. Environmental impact, compliance data, and CO2, carbon emissions, carbon footprint. And all these questions can be answered in our platform. So when I'll be doing the demo later, I'll be sure to show you around how this use case can be shown inside our platform as well. So actually, you make a list of materials, you can see the data from that materials on the right-hand side, and in this print screen that Derya made. Yeah, I will show you this, of course, everything that you're seeing right now in the.
This is our old platform, actually.
Yeah, so this is Derya is a little bit behind. Sorry about that, Derya. So maybe a year or two ago, we actually have a new platform, user-friendlier, much more navigational options, much more data. It will be a pleasure to give you a show around.
Yeah, so it's also critical that when we are making a design or when we are selecting a material, we need to make sure that it is also compatible with the other components. So it's not just like in this drill example. So you cannot just simply go ahead and try to find this material by itself. You can easily find it, but it's working in conjunction with many other components. So we need to make sure that it is compatible. And a very funny example here is that, yes, there is this profile that's been bolted with material, but it started to corrode. So this is like a very failed material selection of a good example of how we should select compatibility of different components together. So again, here is an example from you guys. Maybe you can explain this.
Yeah, we have joined.
Or shall I just?
All the welding, brazing, according to material. I mean, what material you are using. So you need to choose the precise joint for that, because you know, as a material engineer, there is a new mechanical properties you are creating when you are welding a material, right? So it's very important what chemical composition is mixing with what material chemical composition to have a solid connection joint there. We do have a lot of information, joints, and corrosions, and mechanical physical properties, cross references, a lot of information.
So like you said, we have joints data, yes, understanding the chemical composition of the weld and also the mechanical and physical properties of the weld if given by the reference. Exactly. But also we have corrosion data, and that's really, really important. Understanding what corrosion rate you have according to a certain medium, concentration, and corrosion type. Because we have a lot of different kinds of corrosion types as well, which you can choose from as well, including cracking and pitting corrosion types as well. But with the mediums, we literally go from oil to water to acid to ketchup and mayonnaise and beer and whiskey. We have literally hundreds and hundreds of different kinds of mediums which you can choose from to understand if you can use that material which you have chosen inside that certain medium and how long it will take, how resistant will that material be for a certain time period. Yes, so this is very important to understand as well.
Yeah, true. Yes, exactly. And we were talking about some market needs. For example, this innovative approach was, for me, was one of the fantastic innovations in automotive industry, because it's always a weight reduction, and particularly from Formula One teams, there was a need to change the material of this forged steel crankshafts. But it was at the time a very difficult challenge. But with the development of new alloys, so you can have now a hollow crankshaft. You don't need to have a forging, because forging has the highest mechanical properties. But with a casting, with a cast iron, you can achieve the same property that is needed for this specific function. So you have now a lighter. Yes, I guess we have some data from Total Materia. Yeah, so you are now lighter and almost achieve the same strength for this particular situation or example. Yeah.
And the great part is we have a lot of Formula One customers.
Oh yeah.
Yeah. Also. Yes. Yeah, so for actually we are talking about all these informations, yeah, how to select the material, which one to select, which one is proper. So there is a lot of information flying through and too much iterations going through. But occasionally, but actually maybe most of the time, actually there are customers that goes to these providers and they say, okay, I need this product to be produced by you. So they determine all the specification. So they gave you the dimension, they even provide you the manufacturing method, they give you the materials, all the measurements and everything, and tolerances, precisions, and now produce it for me. So that's why there is a general belief that the customer is always right, and the customer always comes and determines everything. So it keeps your hand tight. There's nothing you can do about it. But in my personal experience, customer is not always right, because I'm a foundry man and I work with a lot of foundries. And some customers we came across, I call them, please, no offense to anybody, please don't misunderstand me, but I call them Google engineers. So they come up with doing searches on the internet without the proper tools that we are talking today, not using any of those references or standards, or just Googling in forums and asking people around and trying to come up with, yeah, this is the material we want to use. Yeah, but okay, this alloy has a nice strength, yes, but it is not castable. You cannot cast this thickness with this alloy. No, this is the alloy we want to use, yes. Okay, so you need to convince them that they are not properly true. So that's why you can come up with better ideas yourselves, like we can choose this alloy. And also sometimes, like we have seen in the crankshaft example, actually, maybe I can go a few slides back. Yeah, so, oh yeah, here. Yeah, you see the forge strength of the crankshaft is around 800 megapascals. Cast iron has 400. So it's actually, it looks like it's the half of the strength. But in the analysis, so you need to do a proper analysis, make sure that what you need is correct in a certain design that you are requesting. So that's why I call it the Google engineers and customer is not always right, but you need to have this knowledge and experience to stand up against them and maybe even change the design and maybe even change the alloy. So that's all I wanted to say for today.
Thank you actually very much. Seriously, because estimations are not enough for you to make the design perfectly working. Obviously, you need a lot of data, a lot of information, a lot of experience also. You're facing with the challenges, so they're giving you a lot of question marks. So you are the one who needs to solve all these problems. And actually, I would like to introduce what we are doing. As I mentioned earlier, this is our 25th years online. Total Materia is one of the first reliable digitalized data source in the world. So right now, we can proudly say that we are the biggest source in the world, right? We are covering a lot of information. Plus, we are following the technology. We have AI tools for material information, platform connectivity. We are offering managing internal material informations, enterprise integrations, and as Tim just mentioned, it's not only enough mechanical physical properties, but compliance, sustainability, so many things that you need to take into account. We are accessing, with Total Materia, you can access reference data. We are covering over 500,000 of material here. You have a lot of options, and 80 plus, 82, I guess, right now, standards worldwide, thousands of producers data sheet. You can even build your own internal database with the Total Materia integrator, which we have a lot of clients in that. Also, an AI tool, machine learning with the predictor. You can predict missing properties of the material. You don't need to make actual real tests. That it will make you save time and money, of course. And the green line, very important part. You need to choose the greener material and LCA, your carbon footprint, a lot of things that you need to know. And Total Materia have the answer for all of that. We are covering a lot of national standards, and every month Total Materia is updating so that you will be able to find thousands of alternatives for your design, which we are offering a lot of tools to filter those.
If you go back one slide,
material.
So we have not 80 standard organizations. This slide is a little bit old. We have at the moment 83 standard organizations with 39,000 standards. And the great thing about this is we have standards from almost every country in the world. Yes, those North American standards, those European standards, those Asian standards are really, really important. The reason for this is sometimes you do a design in Europe and you're doing the manufacturing in for example, in China, yes, and you're not going to export all those materials from Europe to China, yes. And what these standard organizations are doing, actually, they connect really well together, providing us with equivalent and alternative materials for every material for all over the world. So what the Chinese manufacturing will probably do is find a really good alternative material which they can buy locally, and they'll probably find a cheaper material as well.
Yeah, yes? Cheaper.
So it's all about saving money, finding the right material with the right properties, with the right corrosion, with the right joints data, understanding the sustainability, is that material compliant, and then carrying on with their design or job or manufacturing, whatever you might be doing. So all of these different kinds of standards are all connected, but also these producer data sheets, yes, they're providing us with missing gaps of information regarding metals, but most of these producer data sheets are also giving us information for polymer data or ceramic or composite materials. Even those producer data sheets also providing us data regarding equivalency, but also more importantly, compliancy as well. Yes, sorry, Zaim.
Yeah, sure. That was the point actually. So that the signations that standards are providing is not clean for different standards. So this is the tool that you can find the equivalent material exactly the designation in different standards. So we're providing a lot of information, and it's not only for material selection, material specialists, it's also for the supply chain. It's important for your simulations, important for your design team and quality team, sales team, product support, and purchasing department. So they all can use Total Materia, and Tim will show us how actually they can use, right?
Thank you, Zaim. So I hope everybody can see my screen. I'm a Formula One fan myself. Yeah, it happens. All right.
Verstappen.
Of course.
Because he's from Netherlands, right?
Yeah, I'm from the Netherlands, so I'm a Max Verstappen fan. It makes kind of sense. You can see my screen, yes? Yeah, fantastic. So this is the platform. I'll be showing you a little bit of live demo today. You can actually see in every data set a little bit all the topics that Derya and Zaim were talking about today. Green line, all about compliancy and sustainability. Predictor is through machine learning, filling up missing gaps of information. And we had also all these other data sets as well very quickly. Total search, looking for a designation, or advanced search and material discovery, doing a material selection. And that's what I'll be showing you today. However, we also have a lot of advanced properties and nonlinear data in our extended range. Data plus all the joints data that Derya was talking about, and in our environment, all the corrosion data that he was talking about. Finding a supplier, a local available supplier, which has those alternative materials or materials that you need, which are maybe cheaper, because inside our platform, we also provide indicative prices as well. We also have SmartComp. Through SmartComp, we can identify materials through their chemical composition, or very simply, you can use this for reverse engineering or even quality control. And all of this data that we have, yes, you can export to your simulation tools, CAD tools, CAE tools, even through an XML format, or if you want, through an Excel sheet as well. Traceability is also very important. Understanding what the changes are that this material has had, you'll be able to find in our tracker. And Material Console is a place where you have full control and you can organize everything that you can do, that you're doing inside our platform. Creating list of materials, saving and sharing everything that you're doing, comparing materials to their materials or properties or diagrams, or through analytics, or you can take any content from the platform, put it inside to a report, add your text and your own information, and then create a report, upload it to a PDF if you want, or share it through the platform to help you justify that material decision that you're making. All right, so let's go back to total search. Yes, total search, we have quick search. It's only meant for designations. You can click on the designation that you need, for example, 304, maybe an ASI standard organization. You click on search, you find the material that you need, and just very briefly, you can click on that and then see the vast amount of information that we provide. Yes, indicative price, very important. The material group as well. References are extremely important to us, that the engineer will have confidence in what we provide is accurate. Yes, we are not a Google search. Yes, Google is probably one of our biggest competitors, which really doesn't make sense. And Google has licensed with us at Total Materia for their only engineers to look at our correct and reliable material information. Yes, so they know their information is not correct. They come to us for reliable data, and that is what we do. Yes, we have over 500,000 materials inside the platform coming from references, real references. Every dot, every comma, every diagram, every point, every microstructure, every diagram that you see in the platform, you will always find a reference where we receive this information from. So in the middle here, references. Yes, at the bottom you can see that we have 177 conditions, again with the references and the conditions, and then below you'll be able to see those properties and those values and the temperatures that we have chosen. Again, the references with the conditions, and again below, just in case if you have not seen it yet, you'll be able to see the references again where we got this information from. Yes. Also, physical properties are cross-referencing table where you can find equivalent materials. And on the right-hand side, of course, the chemical composition, metallurgy data, heat treatment data, including TTT diagrams, CCT diagrams, even some advanced property data, stress strain diagrams.
I think this is because what Derya said. We are designing, and then when customers start using it under the specific conditions, then we know more about that design. This is what extended range it gives you, right?
Absolutely. So advanced properties for the designers and advanced properties in nonlinear data is extremely important. And then, of course, those joints and corrosion data as well. And all of this information you can upload, yes, to your ANSYS, to your Abacus, to your CATIA, to your Creo, to your SolidWorks, Solid Edge, HyperWorks, Excel sheet, XML format. You click on the solver that you need, take the data that you need, and upload it directly on to your tools that you're using for your design, or CAD tools, or any other tools that you're using. So, if you know the material designation and you want to find the reference data from that material, you can fill in inside the quick search the designation and then find the information that you need. Yes. However, we were mostly talking about today about material selection. Yes. It is extremely important, yes, that you find the right material for the right condition. Yes, the right design. So we have two ways to do a material selection. We can start from a clean canvas. If you do not know yet which material you want to use, yes, for a certain design, material discovery is a perfect way to start. Because through the material discovery, for example, if you're inside a automotive, let's stick to the automotive part, you're looking for the automotive, you're looking for a light material, and you're looking for a very strong material, yes? For example, density versus the tensile strength. You can then show the results, and then you can see the groups of materials with their values. So you can see here the composites, you can see here the non-ferroalloys, the ferroalloys, and also the polymers and ceramics. Then you can play around with this diagram and then choose which group of material you need. So you're not interested in wood or foams or honeycombs, nor in ceramics, nor in ferroalloys. However, I am interested in non-ferroalloys, but then I'm only interested in, for example, aluminium, and I don't know, I'm just saying something, for example, titanium.
Yeah.
Yes. And then you scroll up, and then actually the diagram has changed. Yes. So we can see here now titanium and aluminium. Yes, instead of non-ferroalloys. You can scroll down even further. You can open up the polymer parts and open up the composites parts. And then when you scroll back up to the diagram, you can then see the different kinds of polymers and composites as well. You can even open up this further, yes, and the diagram will change accordingly. Now, the great thing about this is once you think, okay, I want to choose this group of material, you can then click on that material, yes, that you want to use, yes, and then forward this onto our advanced search. So you're going from a group of material with averages, yes, from all the conditions and temperatures and values. You're then forwarding that that decision that you've made regarding group of materials and forwarding it to our advanced search. And through our advanced search, you can add mechanical and physical properties or standards or other references to narrow it down that search. So you're going from a group of material to real materials with real designations, with real conditions coming from real references, yes? And of course, getting that confidence in looking at that real data within our platform. So this is the material discovery, yes? I'm quickly going to clear this part and go to the advanced search. If you already know which group of material you're going to use, you can skip the material discovery part and go directly into our advanced search. You can then choose that group of material, for example, structural and constructional steels, coming from a standard, I don't know, DIN standard, let's just use this one to make my life easier. And then you can add some text. For example, automotive, aviation, aerospace, oil, forging, stamping, pressure valve, a boiler, whatever you might want to use to narrow down that search. You can also add some mechanical properties. Yes, do you need impact or elongation or yield strength or tensile strength? And you can add these properties onto the search to narrow it down, that list of materials. Yes. So for example, we can add one more, impact, and then you can choose the units. Of course, choosing units is really important. Choose the type, and then you can choose the values. For example, I want for yield strength to be 300 minimum megapascal. For tensile, I want 800, and for impact, I want, let's say, 40 joule. You can also add the temperatures in different values, in different units, I mean, and we can even add some physical properties as well. For example, modulus, that's a very famous one, and we can say 190 gigapascal. We can add this to the search. The more criteria you add to our material selection, the narrower the result will be. If you bomb this full with information, don't be surprised if the result will be 0. So always start slowly. You can always add more and more criteria on a later stage. So we have found 39 materials inside the platform that have this criteria. Yes, all coming from the DIN standard organization. You can then add columns with properties to narrow down the search. But what you can also do is forward these materials to places within Total Materia. So if you would like to see some advanced properties on your data, for example, stress strain curves or fatigue data or creep data, you can forward those materials to that data set to narrow down the search. For example, you can forward them to the stress strain part and then add strain rate or the heat treatment or the form of that material that you're looking for to narrow it down the search even more. This is the same regarding corrosion. You can add the medium, add the corrosion type, add the concentration to narrow down the search to find that material information that you're looking for. However, what I'm going to do is add to my list. I'm going to add my list to my list builder, and I'm going to save this. Yes. So I'm going to say, sorry, Derya. I hope that I write
Derya. Yes.
Derya. Sorry, Derya. Materials list.
Yeah, that's fine.
Yeah, there we go. And this is a demo of Total Materia. Here we go. So when I save this, my list will be saved inside my console, inside my materials list, and then if Derya wants, he can share this with his colleagues or upload for another time as well. These materials you can compare, and I'm going to go a little bit faster because the clock is ticking, but these materials, yes, you can add to your comparison view, yes, to compare materials all next to each other, their mechanical and physical properties. Go to the left, go to the right, pin down the materials that you need and make a PDF or upload this onto your report. You can also compare these materials through their properties. Yes, you can create a nice radar chart or a diagram with the properties that you need. Or what you can do is forward these materials to analytics. The great thing about this is not only you can compare the properties, but you can also compare the prices as well. We're giving indicative prices of each of these materials for you to give an idea of what the cost might be. But you can also just add the properties, impact versus, for example, tensile strength, press on results, and then you'll be able to see all those materials inside this diagram. Yes, you can even put this into a rectangle to show the full minimum values of each of the materials inside the diagram. You can scroll down, of course, see this as a table as well. So you might now understand which material you'd like to use for your design, for example. However, you still don't know the compliancy and what the CO2 emissions would be of these materials. So what you can do is go back.
Issue. Yeah.
So there's lots of issues to be talking about. So what you can do is forward these materials, or just the ones that you have chosen. I'm not going to do all of them because that's a little bit ridiculous. But I can forward this first to our compliance assessor and then assess if these materials are, for example, compliant to Article 59, so substances with very high concern, and if they're compliant to RoHS, for example, RoHS Europe 2015, and then you can assess these materials to see if they're compliant according to regulations. This list you can then upload onto your Excel sheet, yes, to help you justify your material decision, not regarding your material selection, but also regarding compliancy. But at the same time, yes, you'll also be able to understand what the exact carbon emissions are of these materials, yes? So here we have those few materials, and then we can add the parameters. What is the manufacturing region of manufacturing? For example, Germany, yes? We can say the manufacturing route, let's say EAF. We can maybe lower down a little bit the recycled content. We can add the process, for example, hot rolling, yes? We can add, again, the region Germany, and we can add this to the process. And for example, the transports, well, I'm going with the truck, Euro 3, 200 kilometers, and then I'm going with the train, diesel with particle filter, another 500 kilometers. And then with my bicycle, I'm just joking, but you can add any transport type that you need, save this, and then you simply press on calculate to then calculate the carbon footprint. You can even see the carbon footprint in a nice pie, yes, to know exactly where the most emissions are coming from, yes. You can play around with this as well. And then what you can also do is click on the cross-referencing part and then understand for an equivalent material that is maybe has less carbon emissions. Yes.
Some of those are causing some carbon footprint, obviously here, right?
So you can, exactly like it says, you can then click on the equivalent material, find an equivalent material that has less carbon emissions. Yes. So there's a lot of way to understand not only the material selection, understanding the material that has the best properties for the best price in a local area, but at the same time, understanding if the materials that you've chosen are compliant according to the regulations that you need to follow, but then at the same time, which of the materials that you're using and that you're interested in have the lowest carbon emissions, and if they don't have a lower carbon emission, is there an equivalent material that has? Yes, and that's where I'm going to stop because the time is going really fast. And Zaim is going to kill me because I can talk really a lot about this topic.
It's all about information. Maybe briefly, predictor a little.
Yes, so predictor, I can show predictor as well. Do we have time, Zaim?
Yes, we still have 2 minutes.
Fantastic. So, as everybody knows, yes, there are materials that have missing gaps of information. Yes. What we do within Total Materia is we provide material information coming from references. Most of our competitors have all theoretical data or typical data. Yes, we don't do that. We have real data coming from real references. Yes, if the reference doesn't provide us with mechanical properties, if the reference doesn't provide us with physical properties, through an equivalent material, we can still try to help you. Yes, however, even through an equivalent material, sometimes you will not be able to find those properties. You can see, for example, this material 2075, yes, it only is the reference, the AA standard organization from this official source is telling us we are only providing us with the property density, yes, and some chemical composition. Yes, that is all that this standard is telling us. So if you need information, sometimes we go to the cross-referencing table. That's the first thing you can do. But even if those cross-referencing table, if those equivalent materials are not providing us with the data, you can then use our machine learning. Yes. So for example, we can add that material 2075 to our predictor. We can press on search. We found that material with the chemical composition. We press the next step, and then you can choose the model description. Yes. What kind of information do you are you in need of? Yes. So for example, I am looking, for example, for the minimum value of yield strength at room temperature. I can click on this step, press on predict, and then you can choose the product. For example, I want bars, I want in diameter, thickness 20 millimeters, I want the direction L long, and the heat treatment, the T6 heat treatment condition. And then we can predict. Yes, and then you'll be able to see the information provided within our product. Yes, the yield strength regarding room temperature, and it's fully applicable. Of course, we also have diagrams, but then I need to show you another step, but we can do that for another time.
Yeah, we literally tested a material in seconds,
Yes.
right? So yeah, that's a lot of things to talk about Total Materia, obviously, and we don't have much time. And thank you everyone that you are being with us today, and hope it is very useful and helpful for you. And thank you very much, Derya.
No, sorry, I was muted. Yeah, the pleasure is mine. Thank you for the opportunity. Thanks a lot. Thank you.
Great, great. I have the recordings, and I will share with you, and hopefully it will be very, very useful for you. And good evening, and see you next time.
Yeah, thank you so much from my side as well. If anybody has any questions or they want to follow up, or maybe a quick session to explain some of the other questions you might have, please send us an email. Yes, you can send Zaim or myself an email, and then we'll try and answer all your questions as well as possible. Thank you again, and yeah, enjoy. Keep in touch, hopefully. Thank you again. Bye-bye.
Thanks. Bye.
Take care. See you. Bye.